embarrassingly long amount of time polishing this up, so I'm always happy to show it off to people. So if you want to see the super fast, unedited version of this, there is a link that I can give you that's at the end of the hour spiel where I just give it to the camera. So I'm not going to do that. I'm going to go through all the same content, but I want to encourage everybody ask questions, interrupt. Let's make this interactive, because if you just want to watch me talking and not get any interaction, you can get that on already. So let's get right into it. In case you don't know, my name is Carson Anderson. I work for DOMO. This presentation has nothing to do with DOMO. I just work there. This is all about Kubernetes and understanding Kubernetes at a bunch of different levels. And the original version of this was, I was trying to figure out how to explain Kubernetes to all the different people at DOMO that might be interested. And I sketched out what started with 4 slides of Kubernetes at various layers, right? Kind of like an old overhead projector. The idea is you look at Kubernetes at the top layer and say, oh, you just use it like this. And then you peel away that bit and be like, oh, that's how this works at this layer. And you peel away another layer and you dig, dig, dig. I've since gone way past 4 slides, but it's all the same idea that we're going to focus on one piece at a time, so that I'm not just throwing the inner workings of Kubernetes at your face all at once. Let's get right into it. Alrighty. So, like I said, Kubernetes Deconstructed. I'm going to start at the basic user section. This is everyone hopefully here has done some level of this. This is just making some Kubernetes stuff. Really, really basic, just to give us a shared bit of infrastructure that we've made a Kubernetes thing, and I'll talk about how that works. Then I'll dig into it all further layers later. So the basic user, I'm going to start. Everyone here has used containers, right? Containers. Okay. I'm going to really skip over this. I did this because I might focus this talk in places, but we have something we want to containerize, like this presentation, which is containerized. It really is just a file system. Super simple version of containers here. It's a file system. You box that file system up, you tar it if you're doing Docker, whatever you do for Rocket. Stick metadata on it for runtime information, stick some labels on it so you can get versions, and boom, you've got a container. We've done this probably 100 times all of us. And this is really cool. This is Docker's lowest unit. This is the way Docker wants one application, one container, one process, tree, go. But this kind of doesn't work. You really often people want to run things in tandem. This happens all the time. So you want to run something like a Prometheus exporter next to your application. Let's sit there and watch the application and get metrics and expose it up to Prometheus. You might want to put Envoy. If you're at KubeCon, you've heard a lot about Envoy. The service mesh is the new hotness, and Kubernetes makes it super, super easy to put that on top of your existing applications without a lot of work on your services. And you might want to put a volume in there. And if you're doing Docker, you have to provide a way to run a copy of all these next to each other all the time, and it'd be ugly and terrible. But in Kubernetes, we have pod, right? We're all somewhat familiar with Kubernetes here, or really familiar. So pod can be simple. It can be one container. It can be multiple containers, container and a volume, all sorts of mishmashes of all these different things. This is, like I said, really, really basic, but I want to make sure we're all on the same foundation. So we can run a pod. We can run multiple copies of pods. Stop me if you've heard this before. But I don't want to make pods manually, so we're going to make a deployment. And deployment Kubernetes is going to make all of the pods for us. We'll create a service. We're going to put the service of the pods. We're going to create, this is all in there for the really beginner people, talking about the labels, and I'm just going to skip through this. This is interesting for you guys. Is everybody here using Ingress? Who's using Ingress? Should I cover that? Not everybody. All right, I'm going to cover Ingress next. So we've all used services and pods, nod your heads, hopefully. But this only works inside the cluster. Services are, by their nature, by default, inside the cluster access to your application only. So to get to it from outside the cluster, there's a bunch of different ways you can, and we'll go over these in the network section if you want to really understand how services work. I'm getting there. But what you really want to do if you talk a lot of HTTP, HTTPS, you want to use Ingress. I mean, Kubernetes Ingress is, I'll really dig into this later, but it's just a host, at its simplest form, it's a host name and path mapping to backend services in the cluster. So you define this kind of singular point where you route all the traffic to different hosts and services into one point in the cluster, and then it can get routed based on these dynamic rules to wherever you want to go in the cluster. And that is really, really powerful. You can do a lot of stuff during this transition. So I'm going to make all this. We're going to make deploy a couple copies of this presentation as pods. We're going to make a service that points to those so that things inside the cluster can get to that presentation. We get Ingress Rules that defines, okay, if I've got traffic coming from outside the cluster into the Ingress load balancer, and this is basic user, so I'm going to assume all that DNS traffic stuff's already set up for me. Traffic comes outside the cluster going to a specific host name, it's going to go to the service, and we're going to traverse all the way through and deploy just like this is pretty boilerplate, assuming you've got the cluster infrastructure set up. So to do that, in Kubernetes, we need master, we need a place to go to talk to the master, we need credentials to actually be able to do things with the master. I'm going to use kube-controller. Again, everybody knows this stuff. We're going to use an imperative, we're going to use some declaratives, and it's boilerplate. So like the world's most standard deployment, one.
Heckle number one, the creator of.
Yep.
Yes. Yep. It was very clear. He said that I created kube-control, so I got to name it.
Oh yeah. I spent the entire 2 weeks at KubeCon retraining myself to say kube-control, and then he stood up there and said, "Yeah, it's kube-control." I gotta retrain myself again, and I can only write so many times over that spot before we're through. So wow. Okay,
We'll dump it out.
Yeah. So kube-control, it's like stock standard deployment. We're also creating a service. Note that I'm doing some fun stuff here with the service where I'm not just using the service to point to it. I'm actually using it for abstraction and discovery and load balancing, which is all of the main services are pretty much all three of those things, which is great. So the service is listening on a specific port, but it's going to a weird port on the pod backend. And then the Ingress Rules, this is a super stock Ingress Rule. Basically just says, if you've got stuff coming into this host, coming into the Ingress load balancer, it's destined for this host, anything under this path, go to this service, and this service port is using the abstraction. So we'll take our access, we'll take all YAML files, send it to Kubernetes, Kubernetes can spit out the three things we asked for, and that makes a lot of sense, and it's going to spit out some stuff that we didn't explicitly ask for, but we knew was going to happen, right? We knew we were going to make a deployment, we were going to make pods. There's some funky naming going on here, which I will explain in the next section. But this is like basic user stuff, right? This is like we all do this day one. So let's do it. While I'm doing that, I'm going to I'll chat away, but you can load that up on your phone or your laptop or whatever, and it will be all of the slides. Just you can click them on your own.
For those that haven't been here before, we do have a guest Wi-Fi. It's shaky leaf, all one word, if you need to connect. So.
All right. So. I'm going to run the automated demo because I have 35 minutes of KubeCon. It's going to use kube-control to basically just set up configuration. So it's telling it where the master is, it's telling it credentials, it's using a context to tie credentials to a specific cluster, right? This kube-control is cool because you can just point it at different clusters. You can have it know about 100 clusters and just tell it at any point in time which set cluster and credentials you want to use for access at that moment. Or even per command, you can just override that. It's a multi-cluster tool by nature. So that's all just the configuration stuff to get kube-control working. Now we're going to create some resources. Again, the imperative, making a namespace manually. Then I'm a basic user, so I'm not doing anything fancy. I'm one at a time sending these YAMLs to the API and saying, create this, create this, create this. In the power user section at the end, I do the fancier, more appropriate stuff. This is it. Just create all the things we want, and then check to see if they're up there. And everything's running, and if someone were to reload that bit.do kubedecon, that'll redirect you to the host name, and then it's going to get through and like really, really basic stuff. And again, the only reason I'm even deploying this is so that I can talk about what just happened at all the more interesting layers. Let's do it. Let's go to the cluster layer and do all of the interesting stuff. This is where I really, I gave this to people who've been doing Kubernetes for 2 years and they're learning stuff. So the cluster admin, this was mostly for KubeCon, but it's useful for everybody. I went ahead and put these symbols next to anything that I felt was worth pointing out was extensible, replaceable, or really highly configurable, and it is not exhaustive by any means. It's just things I thought were worthwhile pointing out. Most of Kubernetes is one of these three things, if not all of these three things. Like it's built to be extended, replaced, and configured. So as a basic user, this is what I'm interested in happen, right? I sent all my YAML files to Kubernetes, this nebulous thing, and I got stuff out. But as a cluster admin, I know that Kubernetes is actually a whole bunch of things. And it's not just these 5 things. It's arguably a lot more. If you go download the release, and you start looking through the bins or Docker images, you'll see more than these things. These are just the big ones. If you're doing federation and some of the really fancy things, there's a lot more binaries in the release now. But these are the core pieces. These top 3 are master components, primarily. The bottom 2 are nodes, although you might see some of the masters depending on how you're deploying your cluster. I'm going to cover them all one at a time. Also want to point out that pretty much all of this is pluggable, configurable, replaceable, and I learned at KubeCon that the kubelet's replaceable. There's a project, Rocketlet, that's trying to completely rip the kubelet out and just do its job and talk exclusively to Rocket. Kubelet can do Rocket stuff, but they're replacing it entirely. There's also like a virtual one that's running in Azure, the virtual kubelet that does the kubelet work, but I think at a different layer. So there really should be a plug here. Starting at the top. So the API server in Kubernetes is the thing that we send our YAML to, right? When we send all our YAML files, we ran our kube control commands. We didn't talk to this nebulous blob of Kubernetes. We talked to this component. That makes a lot of sense. We're doing API calls. We're talking to the API server component. This is not a surprise. Notice we've got our first plug here. These are kind of the two big plugins for the API server. Custom resource definition. These used to be called third-party resources. And API server aggregation. And since I have way more than 35 minutes, I can actually talk about these. These are really, really cool. So custom resource definitions is a way that you just you create it. It's just that you define another YAML file, and you send it to the API server, say, Kubernetes API server, I want you to understand a resource that's called donuts. And you can then, once you send that to the API server, you can do kube-control create donut, and you can just throw data at it. And you'll be able to create, update, delete. You can do all kind of the native stuff with Golang client, like it is a custom resource. Kind of, as they were talking, I wouldn't be surprised if in like the next year, the API server gets forked into its own thing entirely. Like they were even talking about how the Kubernetes API server is so powerful and the structure is so good that it almost makes sense to just be able to stick it up and run this as an API framework because it's awesome. So the custom resource is really simply say, hey, API server, I want you to understand resources called this. API server aggregation is where you carve off a subpath underneath the API that gets routed to your own process. So if you wanted, this isn't super flexible, it's stupidly easy, but it's not really flexible. So if you want really tight control, where you still want everyone to go through the main front door of the Kubernetes API server, but you want to handle specific requests, you can use the aggregation. So I'll kind of talk about how that plays into other stuff later. Yeah.
How does that work as far as like plugging into the Kubernetes UI?
Which UI?
Like the dashboard?
Dashboard doesn't know about any. I think they have a place. The new version of the dashboard have a place for the custom resources, like to list them out. But I don't think they have. Kind of have to build their own.
That wasn't very robust either. It just kind of spews out the YAML or whatever.
And they're really evolving this right now. Like they're putting validation in there right now. It doesn't have any built-in validation to the API end. They're putting custom displays, so when you get them with kube control, you can actually show the fields you want it to show at command line level. Right now, it just shows name. But they're really evolving that, and it's so cool, powerful. I wouldn't write a big book at all. But then, yeah, the dashboards don't really know about it. It's almost always used with another plugin that I'll talk about later. So we send our YAML files to the API server, and the API server made stuff. But that stuff doesn't exist just in ether. It has to live somewhere. So in Kubernetes, that's etcd, or an etcd cluster if you're doing it right. etcd, I want to point out, is the data store, the canonical data store for Kubernetes. There was a discussion about like in the early days whether they made it data store agnostic, and they really decided like, no, we're going to settle on etcd to get all these power and features, and we're just gonna standardize on etcd. There might have been projects, there might be projects to swap it out, but this is the one. Also, a lot of the really powerful stuff that you can do in Kubernetes, and stuff that makes Kubernetes so fast and responsive, is really they're just etcd features surfaced up through the API. Like they're not rewriting a lot of these cool features. They're just using etcd to do a lot of the hard work as far as replication, fault tolerance, that kind of stuff. So we send the YAML files in and create the resources in etcd. And that's all the API server is. The API server is just the heart, the veins of Kubernetes. It's not doing anything proactively. It's just sitting there and connecting everything together, and it's how you pass information around. Scheduler, his job is basically, it's actually Nate that made this analogy for me, that pointed this out. Scheduler is the major D of Kubernetes, right? So we sent in our YAML files, we made a deployment, we also got some pods. We know these pods represent at least one container that has to be running somewhere. And somebody has to decide, I've got a couple pods with some containers, and I got a lot of places they could live, where will they go? This, just like Major D has lots of people coming into the restaurant, lots of empty tables, it has to decide who can sit where based on what they know about the tables and the people. So the scheduler is going to hook up to the API server with a watch. I want to point this out. You're going to see this everywhere. Basically, nothing in Kubernetes is doing polling. It's all watching, which is just a publish subscribe model. really just an event system. So the scheduler hooks up the API server and says, I care about pods. Tell me every time a pod is added, updated, deleted. And then as soon as that happens, the scheduler is made aware and can do stuff. So there's no delays for any of this. So he's watching for pods, and when he sees pods that need to live somewhere, that are up but have no place to live, he'll decide based on some rules that you can really govern later. You're gonna live there, you're gonna live there, and that's his whole job. He's just the maitre d'. He just says, you go here, you go here. Cool part of the scheduler is it's really, really highly configurable. There are tons and tons of ways that you can give extra information to the scheduler to help it make decisions about where things can and should live. I'm going to go over affinity and anti-affinity a lot in Power section, but these are ways that you can basically tell a scheduler, when you're making decisions about where this pod goes, here's some information about what it likes, other pods or nodes that it likes or dislikes, and then the scheduler can take that and decide, oh, yeah, I have a pod over here that's running, that's got these labels on it, and you say that you don't want to be anywhere near him, so I will never put you next to him. Or same thing with nodes. You can define affinity and say, this pod wants to be on nodes that have these labels. Really, really powerful. And again, I'll cover it in detail in the Power section. Node selectors is the very old school version of that. It's just like you tell the pod says, I want to go on a node that has these labels. It's not super flexible. It's the simplest implementation because it's just, does this node have these labels? Yes, the pod can go there. Really, you want to do affinity and anti-affinity for everything if you're in any even relatively recent version of Kubernetes. Case tolerations are kind of this way that you can, it's moving on from the old schedulable, unschedulable system in nodes where nodes really only had two states, right? They could either receive load or they could not receive load. Case tolerations is a way that you apply metadata onto the node. It says, if this node is, for example, a taint might be that this node is a master. And so the scheduler, it's kind of, these top two are opt-in things for scheduling information, where you have to put this extra information in your pod spec to specifically avoid certain nodes, for example. Taints are a way that you don't opt, you have to opt, you have to opt onto the node, right? You can change a node, say this node is a master, and you don't have to then go to all your pods and say, oh, make sure you put a thing on here that says you don't want to run on a master. You just go to the pod and say, unless the pod explicitly says, yeah, I'll run on a master, and not go there. And reservations and limits are ways that you define what kind of resources your container needs. So it's a way to say, it has to have at least this much RAM and stop it at this point. So if you don't like all of that, then there's tons. Like you basically never need to write your own scheduler. But if you don't like that and you want even more detail, you can write a custom scheduler. You can rip the old scheduler out entirely, put your own in there. All you really have to do is watch for pods that don't have a place to live and tell them where to live. You can be as smart or as stupid about that as you want. And this is really useful if you have like external information you need to make scheduling decisions on. Most of the time though, you don't want to run your own scheduler. You actually want to run both. This is a really cool feature where you can run multiple schedulers at the same time. And then per pod, you just put a field in there that says, this is the guy that can tell me where to live. So 90% of your workload, you can offload it to the scheduler, which is really, really good. And if you have some smaller percentage of workload that needs to know about some external system, then write your own scheduler and just put those pods at it. So there's lots and lots and lots of options. Yes.
One thing that I've been interested in doing, but I'm not sure exactly, right? Is it a custom scheduler? Is it something else? Is like for having separate node pools that Google has on theirs. And, one of them is their, spot instances or the, whatever they call their version of it. And I've got, workloads where it's, I have 8 hours to process X amount of data, try and run it on this node pool, but, once 8 hours has passed for said work to be done, move it to, a full.
That is a
paid.
hard problem. And that is basically the entire topic of my talk at World different months.
Okay.
Short version of that, what I've done to solve that is I wrote a initializer for pods. It's kind of two parts. I call it it's like a whole QoS system. So every single resource in Kubernetes has a field called initializers. It's just a list of things. You stick an initializer on there, and those resources won't show up to any of the normal API consumers unless they explicitly ask for them. And it lets you, in order, do specific things, including modify the resource before everything else sees it. So I put an initializer on pods and say, until my QoS system reads it, looks at its labels, and decides what kind of nodes it can and can't live on based on what the scheduler knows, the QoS controller knows, then it doesn't show up for like the scheduler or anything else. So it's a complex problem, and probably not worth covering right now, but I can show you more. Most of my container world talk is just that.
Has anybody tried dropping in stuff like Mesos or Marathon? That position?
I don't know. It's a good question. I have no idea. Technically, I mean, anything can replace it. You can replace it with Bash. It can be a simple job, but it turns out to be pretty complex. You want to like actually account for the capacity on the yeah.
So we kind of deal with affinity and contains today. So we have workloads that are big batch things that will have just nodes that just do that. And then we have a cluster auto scaling that will just bring up and down. So you can kind of do it without this, but if you want fine grain, you have to do what you're talking about.
And the reason for mine is because I need to do that differently per cluster without any code change to the end user.
Yeah.
Their end user services are really slow to change. And so I wanted to do it like you just label your stuff. And in my cluster it'll run this way, in your cluster it won't. Like, yeah, you can. You could use taints, and you could just taint the spot instances and say these are spot, they might die if they're tainted. And then very specific workloads that can tolerate that will tolerate the spot taint, and then they'll be allowed to go. And then you pair that with an affinity where you say, this pod would like to run on spot nodes first, and he tolerates the taint, so you'll kind of load into those first and then spill out to the rest afterwards. And if you control the end user code, you don't need to do all my stuff. My stuff is just because I can't change the end user's code. So. All right, so that's the scheduler. We said the maitre d'. Moving on to controller manager. So we made a namespace and a deployment, but if I spent a bunch of time and poked around in the API in that namespace, there'd be a ton of stuff there that I did not explicitly make. Like all sorts of stuff. This is not exhaustive. This is just a sample of extra stuff that popped up. And it is the controller manager that did that. But notice it's the controller manager. And just like a real manager, he's not doing any work himself. He's in charge of people that do the actual work underneath him. There are way more than 3 controllers inside the controller manager, by the way. This is just a sample. There's 20 or 30, there's a ton. Each controller is responsible for one specific piece of logic in Kubernetes. Whenever you say Kubernetes, quote unquote, did something for me, you are really talking about a controller inside the controller manager. Like there is a controller for each action that the cluster is taking for. So there is, I also want to point out there's a plug here. This isn't really a plug on the controller, more as it is like a place that a design pattern and a place some logic fits in. So you'll see the term operator thrown around a lot, like Prometheus operator, etcd operator, there's an Elasticsearch operator. All an operator is some logic that's watching a cluster, looking for either custom resources or default resources in the cluster and doing the logic behind it, right? So back in the API server plug, remember we had custom resource definitions where we could say, okay, I want you to understand resources called donuts. And then you could create donuts in the API and get them and update them and all that good stuff. But that's not super useful on its own, it's just a data store. What you do is you pair that with what's called an operator or just sometimes a custom controller. And all that is something that is hooked up to the Kubernetes API and is watching for donuts, right? So you might have a custom resource called donut, and then you have a sprinkler operator. And it sits there and watches for new donuts. And every time you create a donut that doesn't have sprinkles, it will do something to, maybe in another system, add sprinkles, update it in Kubernetes, like actually make something happen as a result of that data being stored. Because just putting something in the API isn't useful. We can't actually do stuff about it.
So is an operator an actual primitive in
No,
it's its custom resource definition on its own, or is it?
It's just, this is the term that came up for, it's really just a service that's sitting there watching Kubernetes things and making stuff happen based on updates, deletes, changes. It's mostly this is just a name they settled on like instead of controller. I don't know why, but that's what you see everywhere. Okay. It's Core OS, I think, that pioneered the term.
Yeah, the etcd operator.
So if you see operator, it really is, it's literally, for like the etcd operator, it's just a pod running in the cluster, talking to the cluster API. And every time you make an etcd resource in Kubernetes, it goes and spins up pods for you. It's an operator.
Okay.
I think it is built using a custom resource definition.
It is. I have a little tiny preview at the very end of this that has nothing to do with this talk, but it's stuff working on the container world thing, where it is a custom resource paired with an operator doing really cool stuff. So I'll show you kind of the idea at the end. It's the cool stuff. So we have the controller manager with a bunch of controllers inside. They're all sitting there watching for specific things to happen, right? So they're hooked up to different parts of the API. This is not a one-to-one. I just want to show like there's lots. There could be just one. There could be multiple watches in each state. So namespace controllers watching for namespaces, deployment controllers watching for deployment changes, that kind of stuff. And to really break that down, let's kind of go through some examples of how this would work. So as a user, I created a namespace, right? I did kube-control, create namespace. As part of that, there was a controller inside the controller manager that created a service account for me. Since I have time, a service account in Kubernetes is kind of like the Amazon instance role at the Kubernetes layer. It is a default permission set to the API. It's a default credentials, basically, to the Kubernetes API that are stuck into the pod automatically. If you're running with role-based access control in your cluster, then they have no permission by default. But again, it's a way that you don't have to actually like create Kubernetes credentials and pass it to your pods if you want them to do stuff with the API. It's just default key and token and search. So I made the namespace, a controller made a service account. Another controller, because each one just does one thing, made a secret based, saw, oh, we have a new service account, I need to make a secret. I made a deployment. Another controller from those two saw that, okay, you have a deployment, I need a replica set to back that, because you have two copies and deployments don't actually make pods, replica sets do. I do have time, I want to point out the number here is just a hash of the pod spec. So the deployment inside of it has a little field for pod spec, and they just hash that up, and that's where this number comes from. So if you change a deployment and you start listing replica sets that are back behind it, you'll see that what happens is it makes a second replica set. You'll have a new hash, so it's a unique name. It scales that one up and scales the old one down. And if you go list your replica sets, you'll see every version of every change is made for the deployment. That's all rollbacks are. When you do a deployment rollback in Kubernetes with kube control, it just scales down the new replica set and scales up the old one. So, and then another controller saw, the replica set controller saw you made that and made a pod. I want to point out if you guys can see it, then this right here is just a randomly generated token. So all this weird naming stuff just comes from deployment, getting replica set with the hash, and then the other controller taking that and adding this random one so every pod has a unique name. So all that naming actually comes from somewhere, except a little bit at the end of the pod, which is just random. So I made a service, another controller made an endpoints object and pointed it at pods. Just want to kind of drill home that like there are lots and lots of controllers that are each doing a specific piece of logic, and this is the part of Kubernetes that's proactive. And everyone's always asking like, I did this, and now the cluster's doing X, and what logs do I look at to figure this out? The controller logs. So that's it. We have main master components, we have the heart and the veins, we have the scheduler from HRD, and the brain that actually makes things happen. Bottom two are node components. Kubelet talks to the API server because everything talks to the API server, and his whole job is to make containers real. He is watching the API server. There's one kubelet on every single node, and he's saying, API server, tell me when you want a pod to be running on me, and I will make it happen. So in this example, he sees, okay, you want this pod to be running on the node that I'm on. He'll talk to your container runtime and make the container real. That's his whole job. Just sit there, sit on every node, launch containers. And I'll dig more into that in the next section, details. He also does really cool stuff like liveness probes and readiness probes. Just because a container is running does not mean it's still working, and does not mean it's ready to receive traffic. So you can define these probes per container and say, okay, when this responds this way, we're ready to receive traffic, or if this stops responding this way, your process is hung, so we'll restart. There's lots of really cool stuff that he does. But he makes container real, and he's the main interface between containers and the rest of the system. Kube-proxy is the main networking component. I'm going to talk about default networking. You may not even have kube-proxy depending on the network solution that you're running, but default Kubernetes networking is kube-proxy. He talks up to the API server because everything talks to the API server, and his job is to sit on every single node and make services real. Just like kubelet made pods real, kube-proxy makes services real. I will dig into this a lot in the next section, but basically he is saying, oh, you have this kube-decon service and you need to point at these two pods. I will make that real on every single node all the time. And he is watching and waiting for changes. So if the pod changes, he'll make it real. Another pod comes in a different place, he'll make it real. You can just trust that kube-proxy lives everywhere and makes your services work all the time. You can completely swap it out. This is a really, really often switched part of Kubernetes. Tons and tons of ways to do this. You may not have kube-proxy because you might be using different network providers. There's things that use like VPF at the kernel level to do this really efficiently, but kube-proxy is there. That's it. That's as a cluster admin. You know, when I did that, those 3 YAML files and send them into Kubernetes, there's all this stuff that happened to be reactive, to receive that, to store it, to decide where it was going to live, to create all the resources underneath it. And as a cluster admin, that's how I would understand it. Move on to the network section, and my mouse over. Okay, so this is cool as a basic user, but I'm taking a lot for granted in this section, right? I'm assuming that the service just works. But as a network admin, as a network layer, I care about the details of this. So let's dig in. So pods have an IP address, right? Pods represent, like we know, they represent one or more containers, and all those containers share an IP address. This IP address is unique across the entire cluster. Pods live on nodes, because containers have to run somewhere. Those nodes have a unique IP address across the entire cluster. They also, in default networking, have a CIDR range of pods that can live on there. This can change. Network providers do IP address management differently. Like they may not have big chunks, may have multiple small chunks, or it might be pushed out. But in default networking, you've got a node, and if you do a describe nodes, you'll see this is the range of the IP address range that all pods on this node have to live under.
It's node specific, meaning each node has its own CIDR range. Oh,
Yeah. So this is a subset of a larger set. So
cool.
this might be a 10, 00/16.
So etcd keeps track of that, I'm guessing, and it knows how to route based on the CIDR to which node to go to?
Yes, that's super dependent on the networking solution you're using, but yeah, it's mostly in there for all the default networking does things like Amazon route tables and that kind of stuff that says, oh, anything coming out of the cluster destined for anything in this range goes to this node. Cool. And there's a controller manager that talks to the Amazon route tables, for example, and keeps those up to date. But it also, I've seen this pod CIDR stuff done with just like IP route on the host. Like you just go on the host and you can statically define these if you don't have really shifting infrastructure, and it'll work just fine.
Carson, what tells Docker what range to use? Is that up to your network provider?
I would cover that in the network section. Or in the Linux
Oh,
section.
you're gonna
There's
cover
a whole section on the IP address management and how that is determined. So for now, I'm going to assume they got it IP, but yeah, I'll go into that. So I'm going to create a couple nodes, a couple pods, and these pods, cluster's not very good. Everything has to be on the same host, trying to avoid all this garbage by using a cluster system and orchestrator. They need to be able to talk to each other. And this is, I cannot put a singular answer up here because this is probably the most replaced part of Kubernetes. Every deployment does it slightly differently. Like I said, if you're running in Amazon, there's like some stock ways in various cloud providers, but there's tons of ways to do this. There's overlay networks, underlay networks, like just this awesome stuff. I will cover, though, what it takes to be one of those. It's cool to understand the basic fundamental tenets of a Kubernetes network provider so you can understand the promises Kubernetes makes to you as a network layer. So to be one of those tons and tons of network providers, and when I say a lot, I mean, if you go to the Kubernetes install page and you go through all the tabs, that's only like a tiny fraction of what's out there. And there's tabs and tabs of different ways, different solutions for this. But to do that, you need to just do these three rules. If you satisfy these three things, you are a Kubernetes network provider. First one is that all containers, and this is straight out of the docs, when they say containers, they kind of mean pods. They use them interchangeably, but all containers can talk to all other containers without NAT. Basically, we have pods, we have a bunch more pods, everything at a network layer should be able to reach each other directly on their IPs. This is kind of scary at a security layer, but Kubernetes splits those things up. The network architecture is different than the security architecture, and you can run one without the other. So at a network layer, this is the infrastructure. This isn't super surprising for like people in the Amazon world because AWS and a subnet, this is it. Everything can talk to everything directly by its private IP address in the same subnet at least, and use security groups, a separate security layer to define security. Kubernetes is the same way. But a network layer, this is the architecture for pod to pod. So if you do that, second rule, all nodes communicate with all other pods, containers without NAT. So we have nodes, we have pods, everything's flat. You just be able to talk to things directly. Most of this is for administrative stuff, by the way. Like this hop, all these hops here are so that the kubelet can do those liveness probes on the containers. It's not very good to like curl an endpoint in your container if you're networking and get to that container. So that's kind of the fundamental rule. Although it looks like this, they're not side by side, right? Containers live on hosts. But if you make this flat architecture, make it so every node can talk to every container, you satisfy that constraint. The final one is weird. I had to look it up. It's basically don't lunch IP, right? Don't do anything weird. So if I'm looking at my IP address from a process in a container and I think my IP address is X, it should be X to everyone else. Do not make it strange. Do not make it so I think I'm Y and everyone else thinks it's X. Don't mess with it. And docs say they did that so that you could go from a VM into a container and a pod easily. Pods are kind of like super lightweight VMs, so they just wanted to make sure that as a fundamental tenant, you don't screw with your IP address. And that's it. You do those three things, you are a network provider, and like I said, there's tons and tons of ways to do this. So that covers pod networking and how that works. But let's talk about services, because that's the other main networking feature of Kubernetes. That's kind of the core. You don't really have pods talk directly to pods very often. So services can have a whole bunch of ports defined, right? A service has a name. It has a selector of the pods going to at any point in time. It has at least one port, or it's no good. But it can be multiples. They always have to list on a unique one, but they can go to the same one on the back end. That's fine. It's abstraction, load balancing, and discovery all in one. I'm going to focus on a single port. What services also have is a type. I did not put this into the beginning stuff because if you don't specify a type, there is a default, but every single service has a type. There are actually 4. I only put 3 on here because the 4th one's weird and not worth covering, but there are 3 main service types. I'm going to start from the bottom up because they all build on each other. Every single one of these here needs the one below. So when you make a service, if you don't specify the type, it's going to be defaulted to a cluster IP type. And like you would expect, a cluster IP type, there's a controller, the controller-manager that will assign a cluster IP field to your cluster IP type service. That makes a lot of sense. So as an example, we have some web server pods. This is totally separate from our normal pods. We have some web server pods, and they each talk to a cache. I know from the previous section slides that they can talk directly to each other. It's a flat architecture, right? I could go to these web servers and say, your cache host is this IP. And they can get them because it's flat and they can go. But that sucks because what if this pod like scales up or gets deleted or moves to a new host, or it's going to get a new IP, or even just gets deleted and recreated on the same host or get a new IP? You'd have to constantly try to track and follow, and that sucks. So what you would use is you'd use a service, and you'd use the abstraction load balancing part. So I make a cluster IP type service, and like you'd expect, the important part of this is the cluster IP. I point my web server pods at the cluster IP. It's going to go to the cache pod behind it. And this is extremely useful because this doesn't ever change, no matter what behind it changes. It doesn't even have to be, by the way, pods. Services, you can manually point them at IPs outside the cluster. You can just use them purely for name and discovery abstraction, where you can go to this IP and get randomly and get routed to just a set of static IPs on other machines in your network. I want to point out real quick, I'm going to talk about IPs because everything boils down, but you probably, it's optional, but highly recommended running some sort of DNS add-on in the cluster where you can go to the service name, you can go to the service with a namespace, or the fully qualified. All of these are completely valid ways to get to a service. I'm going to talk about the top because everything just resolves there anyway. I also want to point out that namespacing is not security by default. Namespacing is purely logical separation. It doesn't mean that you won't run on the same machine, and it definitely doesn't mean that you can't cross, unless you're doing extra security stuff, it doesn't mean that you can't explicitly cross namespaces to get to services and other namespaces by specifying each one of these two like deeper layers. Like I said, I'm going to talk about IP because everything's resolved there. And again, that's really great because if I scale up the pods behind the service, I never have to reconfigure. I just go to this IP address, and I trust it's going to point me wherever the pods are. Let's take a second and talk about this specific hop at a networking layer. There's one hop going from pod to pod through a service. So I put the pods on their nodes, all their IP addresses match up to their CIDRs, all that good stuff. But what I didn't do, you'll notice, is I didn't put the service IP anywhere. And that's because the service IP doesn't exist anywhere. You can go to every single machine in your cluster and list all of your interfaces and all your IP addresses all day long, and you're never going to find it because it's not on an interface. It is purely there as basically a targeting selector for IP tables. So as traffic leaves any of your pods destined for this address, it's caught up by IP tables and rerouted to all of the active pod IPs behind that service. So you'll never find it on an IP adder show anywhere. But you will find it in IP tables if you do an IP table save. Again, default Kubernetes networking here. Other things might not use IP tables, but this is default. And like you'd expect, something has to keep those up to date, and that is kube-proxy. Like I said, it's the thing that lives on every single node all the time and makes services real. So he made the initial rules in IP tables. If something changes, a pod goes out from behind the service because he goes out of service or gets deleted. He's going to talk to IP tables and take out the rules to make that not point there anymore. If more pods come into service, he's going to talk to IP tables and put them in. Again, you just keep using this singular targeting IP and just let IP tables put you wherever you're going to go. And if you're not running kube-proxy and not using IP tables, the same rules still apply. You just always go to the cluster IP and trust that whatever is doing a networking solution will get you to the right pod behind.
So services have come from a different IP range entirely then?
Yes.
Okay.
When you run the controller-manager, maybe the API server, you don't remember which one of the two, there's a flag. He said, here's the pod CIDR range, here's the service side of it. Cool.
So in your testing, what have you seen as far as load distribution? You're coming out of a pod and and hitting the cluster IP. How is it fairly random?
Yeah, if you go dig and I would encourage you to do this, it's really cool. Go to an IP table save and start prepping for your service name. You can kind of follow the chain. What it boils down to is literally random. So if you have like these 3 pods, the first rule will say you have a 3.333 whatever chance of going here. The next rule in the chain says you have 0.333 chance of going here. Final rule says just go here.
And you end up with a pretty even distribution.
Yeah. So it's IP table is just random distribution.
It depends.
I thought we all looked at that.
So, yeah, we did, and it does do that, but you have to be very careful, because some Java apps, but we've seen that they're not fully distributed, and I'm not sure exactly if they're actually doing some sticky stuff, even though they're not. But definitely what we've seen, if it's like Go or some other good language like it, the applications distribute just cleanly across.
You got some clash.
Well, I know, I always get clapped.
If you're worried about the specifics of that too, you can create what's called a headless service. And a headless service in Kubernetes doesn't have a cluster IP. But it does exist as basically a pointer in DNS, where you can hit the DNS for your service name, and it's just going to spit back at that point in time all of the pod IPs that are currently behind the service, just multiple A records. And then you can client side those out. So you still get Kubernetes like updating DNS as pod change, but then the client end, now your job you can stick yourself to a specific pod. You also have to constantly be checking for changes, and you can't do it.
You can do it, yeah.
Didn't you say that the function was actually called round robin?
Round robin, yeah.
Yeah.
So the same set of IP tables rules exist on every node. So if you have a decent sized cluster, a ton of services,
You will have a lot of items with load. This can actually be a big load generator. We've seen that where we have a lot of load nodes, a lot of services that are changing all the time. You might have a quarter of the CPU eat up just IP table changes.
And they do get out of sync.
Again, yeah.
that still happens.
We don't see it much anymore, but I mean,
I know
if kube-proxy isn't running for any reason, then nothing's updating it, right? Like it used to be actually, by the way, that kube-proxy was here. And he was basically a userland proxy for all your services. And you would hit him and all the traffic would go through him. So if he ever got restarted, all your traffic would get like cut off and you'd have to reconnect. Thank goodness that's not the case anymore. This is actually since like 1.3, this is the default.
Is that kind of in kernel space now?
Yeah, I'd say it was correct. Yeah, kube-proxy used to be the router, and it was a nightmare. It worked to get started, but it was not great.
To answer your question, you set your service IP range and your API.
Okay, I couldn't remember which one. Something with controller, something with API.
You ever tried changing that? Service range?
You might be able to maybe grow it, but change
Increasing it, maybe?
Yeah,
We've had
increasing, you have to increase it.
Yeah, we have some.
Yeah.
Large
ran out.
There's a couple of cluster changes.
Log
that are
services.
big.
That was another run out.
All right, so that's great, all good. Let's move on to the node port. And the reason we want node port is this is great inside the cluster, right? Pod communication. But not everything you're using is inside Kubernetes yet. Or maybe they're in different clusters. And so to reach, for example, our web server pods from the outside world, I need to be able to get there from outside the cluster. And the lowest level feature to do that in Kubernetes is the node port service. So I create a node port type service, a controller-manager sees that and says, okay, every point that you define needs a node port. You can explicitly tell it what you want that to be. If you don't, it'll randomly generate you one. And it's from another really high range as part of the API server controller manager, one of the two, where you can say, here's this stupidly high range. Like you'd expect, node ports to involve nodes. We're going to take that node port, and what happens is when it gets created, when that service gets created, kube-proxy is running on every single node, and he's going to do all the same IP table rules. Basically, just another gateway into the same normal cluster IP type balancing that we had before, but it's a thing that's just listening on that weird high port on every single node in the cluster. Then you can take your client, point them at that node port, and get normal cluster load balancing from there. And a node port service builds on cluster IP, so it will still have the cluster IP, and you can do pod, inside pod routing to that service name, and it will be the exact same routing and mechanisms as traversing into the cluster via the port. That's just a kind of a gateway port that you can have. So you get this really cool. Go to any node on this weird high port and you'll get it. It's super ugly though, right? Nobody wants to send their users into some stupid high port. Like I'm not. Any of you guys do that for the web version of the presentation. So we need one more thing on top of it. So we're gonna do the last bit. Quick note about load balancer type ports. These two are always in Kubernetes all the time. They're really low foundational resources. The load balancer type is dependent on the cloud that you're in, and the way it works changes depending on the cloud that you're in. So you need to look at the docs and kind of get a feel for how it's going to work. But in general, what happens, you create a load balancer type port. It still does everything for the node port and the cluster IP because they'll build on each other. But what happens is a controller-manager sees that, talks to your cloud, makes a cloud load balancer. It listens on a normal port, forwards to that weird high port, and then you can put your clients to the cloud load balancer. And Kubernetes is doing that for you, right? Kubernetes is making this. He's also in charge of, if more nodes come in, he's in charge of updating the load balancer to point at the new nodes. And he makes the cloud resources for you. Like I said, it's super, super cloud dependent.
Is that something that could be, like, if you had a bare metal instance, could I make my own custom load balancer logic? So that it, like, updates kube-proxy and whatever
Yeah,
else?
oh yeah, that's pluggable. So
Okay.
It's not super pluggable right now. They're working on moving cloud provider. Right now, all the cloud providers, quote unquote, that are there are compiled in the controller, but they're moving that to its own binary.
Okay.
On that note, though, if you're on bare metal and you use node port, writing an ingress controller is actually incredibly easy.
Yeah.
So you can just have an ingress controller do the same thing.
Oh, yeah, that's true.
And I'm covering Ingress in cloud. Like this is like one port, one service, which is cool if you have non-HTTP. You don't have to, but Ingress kind of sucks it right now with things that aren't web traffic. So if you have some extra protocols that you want to do non-web stuff, you'll do this. But if you're doing a lot of HTTPS, Ingress controllers are absolutely the way to go. I'll kind of break down how they work in the cloud section.
What if you're too scared to use them on Clint?
What? Don't be. Embrace the Ingress. Love the Ingress. You can do amazing stuff with Ingress.
I thought you were too scared, you had to have HA proxy.
Oh, we still have that.
You do HA-proxy Ingress control. What are you waiting for?
I just want to public
Hey,
identity.
Carson, real quick, at one point, they were, and I don't know if they're still doing this, they were breaking out like the cloud provider into like a separate file.
They are.
Are they still doing that?
Yes, they're doing a lot of work.
It's kind of like weird and I don't know where,
There's a whole bunch of things as they go on that used to be compiled in to various parts that they're now like splitting out to either their own projects entirely that can be updated on a different schedule, or things that are just folders you draw binary. Cloud providers one. You don't really. I would just write something that uses node ports and reads node ports and makes them true before I write a custom cloud provider, right? But what we do for most of our Ingress controllers, we don't make a load balancer type service. We just make a node port service and then make the ELB myself and point it at that high node port. Like I said, you can always build node ports and build on top of that. That's the main Ingress point. But there are some benefits using load balancer types. Like I said, make the load balancer for you. It'll automatically update it to go to the node behind the scenes. You don't have to think about it too hard. So for cloud admin, I'm concerned with where things live, right? We have all these components. We talk about how they talk to each other. We talk about how they work with each other, but they represent code and they have to live somewhere. And in Kubernetes, we split up masters and nodes. Technically, you can have masters run workloads. There are cases where you would, but they're pretty much set out on their own. This is really different than like Docker Swarm, where it's all elected and everything's kind of fluid. Kubernetes really decided like, okay, these masters are going to be special, and you can do stuff to let normal cluster workloads go on them, but you accept some risks that come with that. So we have all these components. They need to live somewhere. I'm going to start with the master components. I'm going to. Yeah, we've been talking for 30 minutes. That was a 30-minute timer. I'm going to describe an HA master scenario. This is super kind of deployment specific, but it's what we do, which is not far off from just the standard HA Kubernetes docs. So we have the API server. We're going to run that actively on all the masters all the time. This makes sense, right? It's just an API server. We can load balance and spread it everywhere. We're going to run the scheduler all the places, kind of. The scheduler code is running. It's there. It's a container usually, and running on all masters all the time. But it does leader election. It talks to the API server. They all three of them talk to the API server, elect a leader amongst themselves, and that is the only active person at one point in time. You don't want two maitre d's in the restaurant telling you to set a shoot up tables. It'd be very confusing. So these three came up. They elected a leader. In this case, it's this guy. These other two, like I said, the code's still there. It's just constantly checking. Did the leader die? Did the leader die? Did the leader die? As soon as he dies, they'll elect amongst themselves, and a new one will take over. That's how you have HA. It's not super high availability. It's fault tolerant, really, not HA, but
Is it raft? Do you know?
they, yeah, they don't talk to entity directly. They talk to the API server, and depending on the version of Kubernetes, they either use like a big map or an endpoint, and they use the API server's lock mechanisms.
Oh, okay.
So it's not even etcd directly, which is really cool. The only thing now that talks to etcd is the API server. Used to be a few more things back there. And then in etcd it's raft. You also have the controller manager that again runs everywhere, but it's elected. So you only want one brain active at a time. So it doesn't have to be the same. No, they're going to all three come up, but one of them is the elected leader. Sometimes it's the same as the other one. Sometimes it's not. It doesn't really matter. You just want one running at any point in time. Like I said, the kubelet are technically node components, but you'll see them on the master almost all the time. And the reason for that is all these other components run inside Docker or whatever your container runtime is. And the kubelet, like I said, is the main interface for your container runtime. So it has this there are cool ways you can do self-hosted Kubernetes where it's a whole talk in and of itself. It's a mechanism where you can just run these as daemon sets or deployments. There's also the simpler mechanism where there's a directory on every master that's got a bunch of prod specs, just YAML files in a folder. And then kubelet starts up and just makes sure all of those exist locally on the system. So he'll run there mostly to make these things run. You'll also see,
So if I've got if I have an HA set up, I've got one API server, so if only one's the actual elected master, and I go ahead and run jobs on that unelected master. That makes sense at all, too.
the API servers are always active all the time. So they're all just talking, they're using etcd as a data source. And
So when people do that, it's three masters and it's all.
So one thing though, in an HA, you really do want to put an ELB or a load balancer in between the APIs and the masters. And then because you have to specify the masters in the API server updates.
Right. So we also run kube-proxy on all of the masters sometimes. Again, because if you're in a really, really high load scenario, sometimes that can generate a ton of master overhead. There's good reasons to run it, there's good reasons not to. You may or may not want to.
Carson, do you ever see, because you can only run one scheduler and one controller manager, that ever being like that service ever getting overwhelmed because you can only run one instance on one node?
Not so far. They're pretty sufficient. Have you seen it?
We've seen it, and then there's some specs as to how many nodes, pods and other things that you're trying to have in your cluster that depends on the sizing if you're in cloud, kind of what instance type you should use for your masters for CPU and also for memory. So we've seen it get up
On
there.
which one? On the scheduler or the?
Well, the master
Just in
node
general.
itself.
Oh, just
The more you want
the
to do.
node.
Yeah, just the node itself.
We also have the node components. Those run on all the nodes all the time. There's no surprise there. Like I said, every single node runs a kubelet and kube-proxy to make containers and services real. So like I said, we also have etcd, right? We talked about that's where the API server puts all of its data. So you might be using some other service, and a lot of cluster systems just bootstrap 3 separate VMs, and they're just for etcd. And then you point the API servers all at etcd, and again, all of this, it does all of the write concurrency management stuff. Or if you don't want a bunch of different VMs, or you want tighter control over etcd, you do what we do, where you run an etcd container on every single master, let them cluster amongst, do normal clustering. You just kind of hyper-converging your etcd and your Kubernetes at the same time. And then you just have the API server talk to every etcd locally. You also, like you were saying before, you don't really want to point people at one of these masters because if one goes down, that's not HA, so we have to reconfigure. So this URL or hostname that you're having people go to for your master is hopefully backed by Cloud Load Balancer. It's pointed at all the API servers, and then you've got your normal load balancer stuff that if this one goes down, then it will stop sending traffic to it. That is the load balancer thing you point your kubelet and kube-proxies at, and it's where you point all your client utilities. Note that this is specifically kubelet, kube-proxies, and the client utilities. If you're a pod going to the API servers, you don't go through the load balancer. You actually go straight to all of the master IPs, and it's still elected, it's still load balanced, but it's done by normal Kubernetes service stuff where you just go to Kubernetes.default service and it will send you to the master IPs stack. So something worthwhile, like you're inside your cluster pod to any pod that's talking to the API server doesn't actually go through this. So I talked a lot about Ingress, but I want to cover how this works, setting it up, not just using it, right? It's basically user just used it and it was magic. But as a cloud admin, I have to do stuff to make this happen. So an Ingress rule is useless by itself. It's just a rule, right? It's not, they'll even tell you first thing Kubernetes if you look at the Ingress page. Ingress rules are just rules. You need something running in the cluster to watch those rules and make them true, right? Just like how kubelet and kube-proxy make services or pods and services real, you need a controller, an Ingress controller, to make Ingress rules real. So I'm going to describe a couple different ways. You'll also use a load balancer and some Ingress controller pods to back up Ingress rules. There's a couple ways of doing this. I'm going to kind of step through the different ways we did it. First one was we set aside a couple nodes. We said these are Ingress nodes, right? We made a separate scale group or some other way to launch nodes, specifically called Ingress nodes. These are normal nodes, by the way. They've got all this. I'm just not showing it. They've got all the rest of the stuff running in there. We then made a cloud load balancer. We used a daemon set to basically run one Ingress controller per node that does specifically for Ingress type. And we use what was called a host port inside the container. That is in the pod spec when you're defining ports the pod's listing on, you can specifically do a host port mapping. And they really don't want you to use this. We did it, but they really don't want you to use it. And the reason is, the whole reason we have orchestrators is so that we don't have to get into port madness, right? I don't want to care that something else on the same machine as me is listing on the same port as me. Like that sucks. We're trying to get away from that. Docker doesn't really provide anything for that natively. Kubernetes does. But again, if you do all this work, set aside some Ingress nodes, do a host port, you do get this really direct, straight hop, which is cool. You go to the cloud load balancer, pointed at a node port service that goes straight into, not a node port, sorry, just pointed at all these subset of nodes, straight at some specific port that's mounted in. Very, very direct and easy to understand, but for madness. So what we moved to, for a lot of reasons, is just a standard node port. The downside of the node port service is you can do this double hop, right? We had a node port service, and we know that once we hit a node port, we're subject to normal cluster load balancing mechanisms. So at the cloud end, you'll get load balance once between all of your nodes. Once you get into the Ingress controller node port service, if there's multiple controllers in the cluster, you will get randomly bounced, maybe to the same machine, maybe to a different machine. You get a double hop, which most stuff doesn't care, but if you're running like really, really sensitive workloads, there may be reasons you want to do port madness and deal with host port mappings, but this is the simplest way, right? You make a node port type service, you create a load balancer pointed at it, or you just create a load balancer type service, again, going to this Ingress controller service to Ingress controller pods.
So Carson, is your Ingress controller writing your load balancer rules, right? That's kind of what it's, or are you doing it differently? Because I know you can have like an Nginx controller that will write Nginx, config.
Yeah, so
but what's writing what?
So this is purely a mechanism to get into the controller. So the Ingress controller pod is some sort of load balancing software, right? So there's an Nginx one, there's kube-proxy, there's actually a whole bunch of offerings of, and what, I don't show it here, but what the Ingress controller pod is, every single one of these is talking to the Kubernetes API, watching Ingress rules, and reconfiguring itself on the fly as those rules get added, updated, and deleted.
Nice.
And so this is purely network traffic at this point. It's coming in from the outside, hitting a load balancer, getting to the Kubernetes service, getting to a controller, which
some sort.
some sort that is looking at those rules and making them happen. So the final step here is then the Ingress controller, like I said, is watching API server. He's watching based on those host and path mappings that you create in Ingress rules, and saying, okay, I've got a lot of traffic coming into me for various things. You, based on your host name, need to go here. You, based on your host name and path, need to go there. And this is how you traverse all the way in from the outside through your Ingress controller to your normal services. Also note that different controllers, the Nginx one specifically, by default, doesn't use the load balancing. It doesn't use cluster load balancing. It actually statically reconfigures itself to go straight to pod IPs all the time, which they say is for performance reasons. It also, it's more performant to not triple load balance, but it also means some of the Ingress controllers can be a little bit lagging behind pod changes. So this is kind of generic.
Is anyone doing gRPC through the Ingress?
I don't know. I'm not. gRPC and WebSockets are two that.
We've tried.
Good website, right?
So the doing and the trying are very separate right now.
It's good at HTTP.
Oh, Yoda says.
So, there's a problem, is we're on AWS and we can't push gRPC through ELB because it's HTTP, not HTTP2. So we always try to put services in the same cluster and then use gRPC using service IP.
Okay. But the ALB would presumably do it?
We haven't. So it's
ALB won't-
There are some wonderful other things with DLP as well.
There's actually, speaking of ALB, I think there's a project either out there or working on for having the ALB be the Ingress controller.
Oh, cool. Yeah, actually, CoreOS and Ticketmaster did that.
Yeah, sure. Do we have a whole talk on that, or someone that mentioned it meetings ago? So there's lots and lots of Ingress controllers. Some that are even outside the cluster. I think F5 can be an Ingress controller and a network solution where it is kind of sits in the cluster and it does the Ingress rules and all your load balancing and all that stuff. So same idea though. The idea is that the cluster usually just create the Ingress rule, and you let whatever cluster you're running in just solve it however it's going to solve it. Like I don't have to worry. I'm creating rules and I let each cluster do it however it's going to do it. So move on to the Linux section. This is where I really dig into the container stuff. So I'm going to cover all these container things because I think they're really neat. Mostly we only need to understand this is Linux kernel namespaces, not Kubernetes namespaces, but there's kind of these three parts that make up how containers work, which I think is good for everybody to know. And interesting.
Carson,
Uh-huh.
we're at the hour-ish time frame. People need to leave, great. Does anyone want to just continue on?
Keep going.
Keep going.
Anyone needs a bio break or whatever, just feel free to go whenever you need to go. I mean, in the bathroom over there. That way.
So I want to use the target section and let me get my little preview of the container world talk.
I'll stay here as long as you want to talk.
Yeah. Oh, well, that's.
I'm sure Paul wants to.
That's dangerous.
Absolutely.
We'll talk all day. All right. So this is basically Linux features that make containers, which you really need to understand kernel namespacing to understand what it does with Docker, but the rest are just neat. So we have a container or really any process, and you can isolate that at the Linux kernel layer in a bunch of ways. You can create a kernel namespace. And you can say, I want to isolate this process as a process namespace, as a file system namespace, as the file system and network namespace. Any combination, really every container you make is isolated in all the possible ways. But that's important not to know that necessarily you can isolate that, because just let the container runtime do that. But it's cool to know that creating and joining are two separate things. It's not a one-to-one mapping. So I can create a network namespace for this container, and to make pods work, I can actually join other processes or containers, kind of using them interchangeably here, into that same network namespace, right? So that's the main Linux kernel feature that makes all this single IP for multiple containers work. I'll kind of break down how that happens with Docker in a second. Second thing is control groups. This is the way that you take all of your resources, basically your CPU memory, divide it up into different sections and allocate that different processes into those sections. So you can also, you don't have to really handle any of this. I mean, this is all handled by Docker and kubelet, that kind of stuff. But it's cool to understand that C group system has been around for forever. Docker's really just a front end on top of all these features. All of the modern container systems are front end on top of these features. You can also take C groups, read the data out of them. It's just file systems. You go cat files all day long and see the information as it's updated, and send it up to your metrics. Which is why basically everything you do Docker metrics, no matter what your orchestration engine is, because it all just boils down to C group writing, not really writing files, but making file devices that you can cat out and get stats from all the time. Kind of fun to know. Final one is unit file systems. So even people use containers all the time, don't necessarily understand the details of this. Unit file systems are a way that you build your container file systems. So you start with an empty space, just a void of nothingness. You build layers on top of it. Each layer has pieces, files, and folders, sometimes the same, sometimes different. A unit file system's job is to take all of those layers, one thing at a time. In Docker, every single time you do a run or a copy or an add or any of those, it's going to make another one of these layers. And it's your unit file system's job to smash it all together and present that to you as one final file system. It also will, every time you make a container, take this base file system, stick a new layer on top of it for that container's runtime, and that's where the container sticks its files. Which is how you get a lot of deduplication in Docker, because you use this bit over and over and over again if you have 100 copies of an image running. the only thing they're really taking up extra is files they write to their own language. Just stuff I think is really cool to learn for containers. Let's break down the nodes. We've already covered kube-proxy, that's all networking, so we're going to talk about the kubelet primarily here. Kubelet talks to the API server, and like I said, his main job is making pods real. So he's watching and saying, oh, hey, someone scheduled a pod on me, I better start containers. I'm going to make an interesting pod just so that we can talk about the details of how this works. We're going to run Nginx, a Prometheus exporter, and an Envoy sidecar. And we know pod, they're all going to share a network namespace, and they can even, take volumes and mount volumes, the same volume to share. So main container runtime for the kubelet is, or for Kubernetes is Docker. So you can use Rocket, you can use all sorts of things. They've made this part really, really highly pluggable, but basically everything is still Docker because that's the most supported one. It's going to say, okay, I'm talking to Docker. You want this really fancy pod running on here. First thing I'm going to do is create a infra container in Docker. Not any of the things I asked for, this weird infra container. And the infra container is the thing that gets the network IP address, right? He gets the IP address, he owns the namespace. His whole job is to sit there and not die. All he has to do. Own the namespace, never die, never need to be restarted for any reason. It's like a tiny bit of code that just sits there and pauses for forever. Then the kubelet takes all the other containers that you want and creates the containers and joins them in the network namespace, the Linux kernel network namespace of the infra container, so that they can all share that one IP address. And again, they can get deleted, recreated, restarted as much as they want because it's this guy that's actually holding on to the namespace they're joining in over and over. Again, the invert's job, his whole job is to sit there and hold the IP. It's also the reason that if you go onto any of your Kubernetes nodes and you do a Docker PS, you'll see about twice as many containers as we thought you were going to be on there because every single pod has one of these, and the keys that you wanted it out of it.
Hey Carson, if you zip into each one of those containers, that you see that same IP address? Okay, that's right.
Yeah, if you type here, you'll see that IPS. They're all, and moreover, they can talk to each other on local host. Really, really cool. So you can actually, sometimes you might run an extra container in here that is, I don't know, doing something, and you don't want the rest of the cluster to even be able to reach it, but you want another thing inside of that pod to be able to reach it. You can hit it on local host because they're essentially, like I said, pods and Kubernetes are essentially ultra lightweight VMs.
Your environment variables actually sequentially then be added to that environment as well. So you can,
Yeah, it's pretty cool. So where did this IP address come from, right? We wanted to figure out like how, that's great. Every pod has a unique IP address, but what's generating it? And Kubernetes has CNI. CNI is just an open standard for IP address management. It's actually something that came out of Rocket that is implemented and pulled into Kubernetes. What happens is the kubelet talks to CNI, and you just have, basically at the node level, you have a bunch of binaries, config files that say, things coming through here, here's how I want you to determine its IP, with either calling these binaries or calling them in these order, running all these different functions. It's super, super highly pluggable. So it'll talk to CNI, CNI will do whatever it's configured to do to get the IP address, give that back to the kubelet, which then can talk to Docker and make that infra container. And then, like I said, it's going to join all of the other containers inside that network. That's great. I do want to talk about Rocket. Rocket is great because it is open source. It's got a lot of features built into it natively that Docker doesn't. I'll go over some of that in a bit. One thing you can do is you can do the normal CNI song and dance and let the kubelet do CNI for you. But like I said, it actually came out of Rocket. So Rocket can do the CNI natively. Instead of configuring the kubelet for CNI, which just, like I said, config files and binaries, you can let Rocket do that and let the kubelet not even care. You can also do really cool stuff. One of the big, huge, mind-blowing differences for Rocket when you first start using it is it's pod native. This whole thing that the kubelet's doing, Rocket's probably doing something similar, but Rocket knows pods as a fundamental resource. You can just say, like, here's a Rocket, I want you to spin off a pod that has 3 containers. Rocket knows how to do that from the get-go. It's just built right in. It's also, when I say spin off a Rocket container, it is daemonless. There is no little Rocket thing sitting here because there is no long-running Rocket name. It's just file systems and processes. So you send it on its merry way, and then if you want to look at it, you go list your file system, and you can see what's running in Rocket that way. If you want to spin another Rocket pod, just spin off a Rocket pod. None of that whole joining, you just let Rocket do whatever it's going to do. Last thing that's really, really great, and you can do this at a per pod level in Kubernetes, is you can say, okay, you're running Rocket. If you're running Rocket, I want you to run the Rocket pod in a VM hypervisor. So you can run all your normal mechanisms, but Rocket will actually start the pod inside a super lightweight VM. And this can be different for a node, by the way. So you could have one node running the kubelet talking to Docker and another node running the kubelet talking to Rocket, and more or less handle them the same way. There's some gotchas. There's a little page on the instructions about kind of gotchas if you're running Rocket, which I'll kind of get into, but there's a lot of really cool stuff. Like if you're somewhere where you can run KVM and you're worried about container isolation, you can get a lot of free hypervisor trusted isolation.
Isn't this how Intel's doing their clear containers?
It's
Similar.
It's something similar, yeah. Intel's got their own process and some sort of hypervisor stuff on top of. You can treat it like, right? When you make this pod, you treat it like a normal pod. You would just give a little metadata to Kubernetes that says, oh, I want you to run this one inside of a VM. And there's some downside, right? That can give some like boot up time and whatnot.
So you're obviously pretty high on Rocket. Like, when would you choose to switch to it?
We're still on everything on Docker. I'm watching it, right? And I like a lot of the ideas that it's doing, but I haven't really dug into it a lot yet. Mostly, like I said, I built this for UConn, CNCF, right? Like, so it's like, I wanted to pull in as much of their stuff as I could. We were looking at it a lot because of this. The downside is if you're on Amazon, you can't do this. It's a no KVM on inside of Zen.
So if you're using CoreOS underneath, it depends on, but we actually use Rocket to run some of the things on the master nodes. So
and you can run them side by side.
you can run them side by
You
side.
can run Rocket with Docker.
But we don't run Rocket like what he's talking about on all the nodes, but we could, but on the masters.
What made you choose that, and what made you not switch everything?
It was because of CoreOS, when we talked to them and how they do things.
Still a lot of cool stuff, right? Like the big pod native, but supporting C9 stuff really. Still a lot of stuff for Rocket. There's downside to not having the one-line data, which I'll get into here in a second. We'll talk about logs. So we can use kube-control to get logs from pods actively. So you be your developer on your machine. You can say, I want to get logs from a specific pod. It's going to talk to the API server. It's going to reach out to the kubelet. The kubelet's going to reach out to Docker, and it has to be Docker. That's the downside of Rocket. It's no long-running daemon, no connections into your containers. In fact, getting logs at all is kind of a pain because everything just goes to serial ports or serial sockets. But then Docker is going to hook up to your containers, stream all that up, and we get it from kube-control. So I think this is just useful because we all do this command all the time. But it's kind of cool to know like the actual process. You're hitting the API server is calling into the kubelet, and the kubelet's then talking to Docker, which is streaming all your stuff down. The other thing you might want to do is sometimes just getting it actively isn't super useful. It's great for debugging, but it's not great for figuring out what happened when you weren't watching. So you can do Kubernetes logging. Basically, anything that does Docker logging can do Kubernetes logging. Hopefully, you've got something, any log driver for Docker that will eat up the Kubernetes metadata, stick it onto all your messages, and send it to your system. There are lots and lots of ways to do this. The main way right now is fluentd. That's the one that you like really push because it's a cloud native project. But fluentd is something you just run as a data set on every single node. It's watching all the container logs. It knows how to talk to the Kubernetes API server, or at a minimum, read the container names, which have a lot of information just in the name, and attach that to every message and send that up to whatever. If you haven't looked at fluentd, it's really cool. But just I kind of put this up here because people ask like, how do you get logs out of Kubernetes? Anything we can do Docker logs, hopefully just grab some metadata on its way out. So in the power user section, this is where all really fun stuff happens. So I'm going to run the power user demo, which adds a bunch of features onto, basically adds a ton onto the normal deployment without changing the image at all. It just adds features straight to the application through Kubernetes. So spec power demo. I'm a power user, so I'm going to do apply. Right? I'm not going to call every single one at a time. Apply is kind of a super powered create or update command. It also it'll complain if you're applying on top of things that weren't made with apply because it'll do ifs. And it'll actually notice like, oh, you took away this thing that you applied last time, let me clean it up. It can do not just additive stuff, but subtractive stuff. So we go. So like I said, I just redeployed. What's going to happen is if I do a space kube-decon. Okay. I should take a second to show you guys this. should be redeploying. And I'm even going to pull up a So the first time we went to this, if we go, we can still go to the normal host name, and it's going to go to the main presentation. But if you go to the /markdown, it's something that I've added in that's not in the image. It's actually just basically adding a bunch of features into my web server dynamically. So if I go look at what I've done here, I'm using a config map to define a bunch of configs for my caddy, which is the web server that runs all of the presentation. So I'm defining a bunch of extra paths, proxying to different things inside the cluster. I'm defining the markdown, which is the caddy feature that says everything under this directory is markdown. I'm also defining all the markdown itself as a config map. So I'm then taking all of that in the deployment, and let's scroll down, Infinity. Mostly this, you guys can look through this later, because I'll go through a lot of this in the power user section, like features. And if you don't want to just know what they are, but how they work, actual practical examples, like dig through this YAML. We'll go down here, and let's see here, I'm mounting markdown. Basically, I'm mounting all the caddy config files in one place. I'm taking all of the other config map that represents all my markdown files and putting it in another place. And so I've added features into the service without, into the service without having to actually change the image at all. It's still just kube-decon latest. I think that's pretty neat. You can also see basically all the features. So if I go here, I can proxy through, and I'm adding kind of just, all this is here so that as I go through the power section and I point out things, you can go dig into examples of how all that works. So this is just a grab bag of fun Kubernetes stuff that you'll put on top of the basic deployment. As a power user, these are all the extra features. I will often run into people that have been spending a ton of time like working on some thing, and I'll look at them and go, no, just do this in Kubernetes, and it does that for you for free. Like, you don't have to rewrite all of this. So one of those things is security context. This is something that you create inside the pod. It's part of the pod spec, where you can define either at a pod layer or a container layer different execution layers. This is all runtime execution information for container runtime that says stuff like run as a read-only root file system, run whether or not you can even run the container as root, what user you want it to run. If you don't want it to run as root, but you need like one very specific root privilege, you can add Linux capacities on top. There's a whole bunch of these things. It's just runtime information says run this pod or this container. Here's execution information. So this is how you would define nothing in our cluster runs as root, or this thing can write to the root file system.
Does it run as root by default?
It works whatever your container image is by default. So if you, this is kind of good because you can have the pod layer say like, I want to run as non-root by default, and then it doesn't matter what the container does, you're going to run as a specific user. So it's all based on the container, and a lot of containers still run as root. So you create that, you apply it, like I said, either the pod or the container level, and if you go look through those markdowns, you'll see security context in the basic deployment YAML. Network policy is that way that you take this really scary, flat, simple, but scary, flat network architecture and define rules that say, okay, things with pods with labels like these can only talk to pods with labels like these on these ports. Right now, that is by default just layer 3, so you can do layer 4. Sorry, I'm coming off the whole. I'm still like so. So you can say you can go to the TCP layer. You can say go to these ports, but there's actually stuff being added on right now where you can do it at lower layers. You can actually do it at layer 7, where you say, okay, pods with these labels can talk to pods with these labels, and they can only hit this port and this specific do gets on this specific path. It's really, really cool stuff. But again, it's network policy. It's just an extra resource that you add into the cluster. It's called network policy. And you define all those rules, and you have to presumably have some sort of network solution in there running that applies those. The default pretty much everywhere right now is Calico. That is what Amazon's using as their, not their standard networking layer, but as their security layer. And it's Calico is something that talks to Kubernetes and just makes IP tables rules that make all of these security rules happen. So there's, like I said, there's examples of that in YAML. Downting API is cool. It's a way to take a a bunch of cluster metadata and stick it into the container at runtime. That is when I clicked on that proxy earlier for the Nginx, and you went through the web server that's running the application into another Nginx pod. The Nginx spat back like, here's my pod name, here's my host name, and it got that information with a download API. We just populate environment variables with not just these, there's actually a ton. You can actually populate it with labels and annotations even. You can get a ton of information into your pods about their runtime through this. I didn't cover config maps and secrets a lot in the presentation. They're both just key value data stores that are handled slightly differently in Kubernetes. But you can take those and mount them into your pods as volumes. You saw that with the YAML, where I put some markdown into the application, and it came out of a config map. So if you look at the config map, there's just keys and a bunch of text, but it's actually presented to the container as a file. Just every key in the config map is the name of the file and all of the values of the content. You can also do, this is really, really traditional, you can take config maps and secret values and use them to populate environment variables in your pods. So that's how you get all your configuration. Yeah.
When it's mounted as a volume, or I guess is it watching and updating?
It is, yeah. It's not. I looked at this, right? It is not instant. It is eventually consistent. There's a third, depends on it's configurable, but like 30 to 60 second kind of interval that it checks and updates. But you can. I did this. You go edit your config map, and in about a minute, it'll be live.
Yeah, so it's true for config maps, but not for secrets.
Really?
Yeah.
Secrets don't update?
Secrets don't update at all
Oh, there you go.
until the pod restarts or whatever.
Okay. Well, config maps definitely, yeah, they do eventually. Right. There you go.
So Carson, how do you guys, 'cause I know secrets aren't really secret. I mean, they're encoded, right? So they're not like encrypted. You guys do something to encrypt your secrets and not decrypt, or
Not
does anybody do that?
There's some work in Ingress
You guys do?
So 1.8, they're default encrypted on etcd.
Yeah.
Well, on it.
Yes, yeah.
They're like search accounts. They're more of this hopeful future-looking thing. They're like, we're going to create a thing called secrets. And right now, they're not. But the infrastructure is there, right? So you can find that with, the new versions where it is encrypted in etcd, plus good role-based access controls, and they start to actually become more secret.
And it sounds like cloud providers like either, I don't know what on that AWS, but like kube-controller-manager or something, or whatever it is in AWS, or integrating with that kind of stuff.
Some are.
I would hope they would at some point where you externally store your secrets.
We like vaults as well.
Yeah.
So kind of separate. But the reason I was saying on the 1.8 is, it may be encrypted, but where's the key?
Right.
Yeah, I'm not sure. That's a good question.
Where's the key? Right. That's easy.
Like, so you can also take them and populate environment variables and not change at all. Affinity is, I just wanted to point out, that's one of those scheduling features that I think is really cool. I have a bunch of examples of that in the YAML. Affinity is a way that you just give the scheduler extra information about pods and how they relate to each other. And so, for example, there's a hard affinity. We can say required. Say, if this pod is running anywhere, and you're trying to decide where to put this pod, you has to be somewhere with this one. So that you can trust that they're always on the same node. So the scheduler deciding where you should run is saying, well, this one always has to run next to this one. He doesn't move it around, but I just want to understand that they're always, when you quite tightly couple them, they're always together. You also have a soft affinity called a prefer affinity, and I don't have the names. You can go look at the YAML. They're really long, ugly names in the YAML. I don't know why, but like required during scheduling, ignored during execution, it's this ugly thing. But it's just hard and soft affinity, saying these have to run together, or try to run these together, but you can split them up if there are reasons that there's not enough space or whatever for these two to run. You can do the same thing with nodes. We can say this pod has to be on nodes that look like this, or this pod would like to be on nodes that look like this. Again, this is different. You have the node selector, which is the old school way, but that was like specific hard requirements, whereas you can do these kind of preferred weighted stuff with affinity and anti-affinity. Anti-affinity is the exact same thing. It's just the opposite, where you can say these things should never run together, or these things should try to not run together. And same thing with nodes, where I say this pod should never be on a node that looks like this, and this pod should try not to be a node that looks like that. Most of this node affinity stuff is used if you've got like specialized hardware, if you've got like instances that are burstable and might go away, and you want to keep workloads off of them. You might have a hard anti-affinity that says this pod will never go on an instance that's burstable because I can't handle having it running. Or this pod would like to, go on an instance that is burstable because I don't care. So that's power section. I'll go over the credits and then I want to show you my little awesome stuff for my next talk. Sozi is the presentation software I use. It's super cool. It's open source. You just make an SVG and then you open it in Sozi, which gives you kind of like a video frame editor. You can animate all the layers together independently and it spits out HTML and JavaScript. Cool. All the logos put on here. I don't know if I have to, but just to be safe, all the logos I use are properties of their respective companies. And
GitHub's good with it.
are they good with it? Yeah. I don't know. Just in case. Okay, there it is. And then the art is awesome.
Sponsored.
There's like a lot of the art in here was just me taking and modifying and or very stealing. Not stealing. Here's all the links that you want. So this is the like super slick 1 hour version of what I just did. Just a video. And then the various links gave them different parts. And I'm sure that'll be in the end.